Suppose at this moment we light a candle. The faint glow it emits will continuously scatter in all directions, forming a slowly expanding bubble that will envelop us. To escape this bubble, we would have to exceed the speed of light. But suppose we are in a two-dimensional space. The bubble would then become continuously expanding circular images. By stacking these images together, we would see a cone-shaped figure growing over time. This is what we call the visible time trajectory. Furthermore, we can see that the inclination angle of the cone's sides is 45 degrees. This is because, within any fixed amount of time, the distance light travels is constant. For example, in 1 year, light can only travel 1 light year, never more. This object model formed by the trajectory of time passing is called a light cone. It always expands at the speed of light, and no matter what we do in the future, we are bound and restricted by the light cone. Unless we can surpass the speed of light and break the rules, we can never escape. In Einstein's theory of special relativity, the light cone is crucial for understanding the universe because it restricts causality. To give a simple example, suppose that at the same moment but in different locations, a superplanet located 2.5 million light years away in the Andromeda galaxy suddenly explodes. Before its light cone reaches Earth, humanity would be completely unaware of this event, and it would have no effect on us. Because nothing travels faster than the speed of light, only when Earth enters the light cone of this event can humans on Earth see the explosion that occurred 2.5 million years ago. Why do we say the light cone limits causality? Because the fact that one event triggers another is ultimately affected by the limitation of the speed of light. Additionally, the light cone helps us better understand the differences between the concepts of time and space. We all know that time and space are considered the two fundamental principles of the universe: infinite time and infinite space. Combined, they form the existence of infinite spacetime. So, what is the fundamental difference between time and space? Here's a simple example. We can move freely in space, forward, backward, up, down, left, right. But under the intangible influence of time continually moving forward, all objects are ultimately forced to move along the direction of the time trajectory. In other words, time cannot flow backward. Unless you can surpass the speed of light, you can only move from the past toward the future. The magical aspect of the light cone is that it allows us to clearly see and understand this difference. This is the mystery of the fundamental laws of the universe. To simplify, imagine a region in the universe where there is no gravity and is completely vacuumed. Its space and time are straight and uniform, forming a symmetrical grid. The light cones are all aligned in the same direction. Therefore, we can unify all the light cones along a perfectly straight line from left to right. However, according to general relativity, once gravity is involved, the direction of light cones seems to change. Suppose we drop an apple from high above the Earth. Under the influence of gravity, the apple keeps falling downward. Let's say the apple emits light. As time passes, it also emits bubbles continuously. But this time, the bubbles will be affected by gravity, being pulled toward the Earth. As it gets closer to the ground, the light cone no longer moves in just one direction, but gradually curves toward the Earth. This means that time itself bends toward the Earth's core. What does this illustrate? It shows that mass can distort the geometry of the universe. Time and space start to become relative, and their directions depend on our position. This is Einstein's theory of general relativity. The greater the mass of an object, the greater the curvature of spacetime. If there exists a terrifyingly massive object in the universe, and if we light a candle near it, all the light, no matter which direction it is emitted toward, will be completely redirected by the curvature created by this massive object, ultimately all converging to the core of the curvature. This object is what Einstein predicted, a black hole. On the evening of April 10, 2019, at 9 p.m., scientists released the world's first photograph of a black hole, thoroughly proving the existence of black holes in the universe. This also demonstrated Einstein's visionary genius from another perspective. According to modern scientific research, a black hole is a spherical curvature in the universe where the curvature of spacetime is so intense that it can pull everything, including light, into its core. If we view a black hole from a two-dimensional perspective, it appears as a stationary circle. But when we piece together the cross-sections of its time trajectory, we discover that it is a cylinder. This means that over time, light does not spread, but instead remains confined within a certain range. The boundaries on either side of the cylinder are the event horizon. Above the event horizon, some light can escape, but once it crosses into the event horizon, all light can never escape again. The light cone forces all paths of matter to point downward, meaning time itself points toward the black hole's center. If that explanation is still unclear, let's use another simple example. Suppose there's an astronaut about to fall into the event horizon and a spaceship parked far away. For you on the spaceship, the black hole's gravity is weak, and the surrounding spacetime is almost flat. The spacetime grid appears smooth, and time moves in a straight line from past to future. But for the astronaut near the black hole, it's completely different. When they touch the event horizon, they are unaware of it. But from the perspective of an external observer, spacetime appears tilted at a 45-degree angle. For the astronaut, spacetime has long been distorted beyond recognition. It's no longer a straight line, but a diagonal line ascending at a 45-degree angle, like the surface of a light cone. Although the black hole appears completely still from the spaceship's perspective, time and space are already skewed for the astronaut within the event horizon. The nature of black holes is similar to light cones. This also explains why once you enter the event horizon, you can never escape. Because you cannot exceed the speed of light, you are confined to the path of the light cone. When the astronaut fully crosses the event horizon, compared to you far away on the spaceship, the concepts of time and space have actually swapped. Time now points entirely downward. The black hole's event horizon is no longer a region of space within the universe, but rather a moment in the past. The black hole's center is no longer a point, but our inevitable destiny. Because the ultimate path of time, its final destination, is within the core of the black hole. This is the marvel of general relativity. Without exaggeration, Einstein's theory of relativity perfectly explains the operational laws of the universe, including concepts like parallel worlds, time portals, wormholes, black holes, singularities, and space-time folding. All of these concepts originate from relativity. Now that black holes have been confirmed by humanity, how far away can the rest of these ideas be?